All right, welcome everyone. So in this video, let's take a look at some examples of sets of vectors in R3. Here we have two different sets of vectors, and for each of these sets, we are going to consider whether or not that set is a basis for R3. And so we've already seen one basis for R3, which is the set of E1, E2, E3, the standard basis for R3. But we certainly can pick three other vectors, and they might be a basis for R3. So just recall the properties that we're going to be looking at are, do these vectors span all of R3? And secondly, are they linearly independent? And if they satisfy both of these conditions, then the set of vectors is considered a basis. So these are the questions that we need to consider. And these are ideas, span and linearly independence, right, that were all over the inverse matrix theorem. So there are lots of ways that we could try and prove this. Really what we want to hone in on is this linearly independence part of this definition. And so by the inverse matrix theorem, if I have a set of three vectors in R3, different ways that we can determine they're linearly independent. For example, we could take a look at the matrix that we get when we look at these three column vectors, and we can think about, well, does this matrix that we get when we combine these three column vectors, does that matrix have a pivot in every column when we write it in its reduced row echelon form? Is this matrix invertible? So if the answers to these questions are yes, then we know that this set of these three vectors are indeed linearly independent. So for example, we can take this matrix whose first column is the first vector 3, 0, minus 6. The second vector in our set gives us the second column of this matrix, minus 4, 1, 7. And then the last column is the third vector in our set, which is minus 2, 1, 7. So then we can take this matrix and, for example, write it in reduced row echelon form. And I will put a link to a Colab notebook in the description of this video that goes through and expresses this matrix in reduced row echelon form. And at this point, I can see that yes, this matrix does have a pivot in every column. So these three vectors have to be linearly independent. Similarly, we could say that this matrix is row equivalent to the identity matrix, and thus it has an inverse, and that would mean that this set of vectors is the column vectors of this matrix are linearly independent. And in fact, we could also take the determinant of this matrix, and we get 6, and since the determinant of this matrix is non-zero, we know this matrix would be invertible, and therefore we know that these column vectors would be linearly independent. So we could use the determinant here and not even go through row operations to determine that these three vectors are linearly independent. And we have three of them. And so if you recall for R3 that having more than three vectors was too much, having less than three vectors was not enough. But if I can find a set of three vectors that are linearly independent from each other, then this would be enough, the perfect amount of vectors to set up our basis for R3. So these three vectors in our first example, 3, 0, minus 6, minus 4, 1, 7, minus 2, 1, 5, they form a basis for R3. So we had the standard basis, and now we have a second basis for R3. And now let's consider the next set of three vectors that we have, which is the first vector is 0, 2, minus 1. The second vector is 2, 2, 0. And the third column vector is 6, 16, minus 5. And we ask the same question, do these three vectors form a basis for R3? And we've got three of them, so that seems like the right amount of vectors, but we need to check to make sure that these vectors are linearly independent from each other, using the same sort of observations that we made about the inverse matrix theorem in the previous example. So I could take this matrix of column vectors 0, 2, minus 1, 2, 2, 0, and 6, 16, minus 5, and write this in reduced row echelon form. And when we do that, we get the bottom row is all zeros. And we actually don't have a pivot in column 3. So columns 1 and column 2 are pivot columns, but we don't have a pivot in column 3. So this means that these 3 vectors are in fact linearly dependent, and these numbers 5 and 3 are significant because they tell us exactly the weights that we need to apply to the first 2 vectors in order to combine them and generate the third column vector in this matrix. So if I take 5 times the first column vector, 0, 2, minus 1, plus 3 times the second column vector of 2, 2, 0, and we add these together, that gives me exactly this third column vector of 6, 16, minus 5. And since this 6, 16, minus 5 is a linear combination of the previous 2 vectors in this set is linearly dependent, and therefore it cannot be a basis for R3. So this first set of 3 vectors was a basis for R3. This second set of vectors is not a basis for R3.